Okay, so hello everyone. In this video, I wanted to show you or explain how can you compute the power in an AC circuit. Okay, so you can compute the power of any element of a circuit by multiplying the voltage and the current, that passes through the element. Okay, so you can compute the voltage using this relationship. But remember that in an AC circuit, we have a sinusoidal voltage, okay, that can be expressed in the following way. Okay, this is the expression for the voltage, and this is the expression for the current. Okay, and well, if you multiply these two expressions, you will obtain also sinusoidal waveform. In fact, you will notice that you will obtain um, the sinusoidal. Okay, and in fact we can divide the behavior of the power function, okay, that is the result of multiplying these two functions, the voltage and the current function, into two components. We have an instantaneous component and also a DC component or a constant component. And this constant component is what we call the average power. Okay. So the constant of this sinusoidal or the offset of this sinusoidal is what we call the average power. And the instantaneous power is basically the varying component, no? Or the component that changes with time. But typically, we do not compute this instantaneous power because this power changes with time, no? It depends on time. So we want to, instead of analyzing the instantaneous power, we want to compute a metric that does not changes with time, okay? And that component is the average power, okay? And you can compute the average power of any component in a circuit by the following expression. We can say that the average power is equal to 1 over 2 times the amplitude of the voltage times the amplitude of the current times the cosine of the phase angle of the voltage minus the phase angle of the current. Okay? With this expression that is equivalent to this constant value, we can compute the average power. Okay? And also, you will notice that the average power of an inductor and a capacitor is equal to 0. Okay, so the average power of an inductor and a capacitor is equal to 0. Okay, they do not consume, they consume power. Okay, but they do not have an average value. Okay, that basically means that we don't have offset in the power function of these two components. Okay. So these two components do not have average power. Okay. In fact, you can use this expression in order to compute the power of a capacitor, for example, and you will notice that expression will result in a 0. Okay. So in this case, we have the following circuit, no? And they are asking us to compute the power of the voltage source, okay, of this voltage source, and the power of the 4 ohm resistor. Here we don't need to compute the power of the capacitor because the average power is always equal to 0 watts, okay? There is an instantaneous power, okay, but we typically do not analyze it because it changes with time and we want to compute a metric that is invariant to translation, no, or to time. So, well, how can we compute the power of the voltage source and the resistor? Well, we can apply the Kirchhoff voltage law. So if I apply the Kirchhoff voltage law to this loop in order to obtain the current that flows in this loop, we can express it as follows: minus 5 with an angle of 30 degrees volts. Okay, remember that since the current is entering through the negative terminal, um, well, we are saying that the voltage is negative. Also, we will make the assumption that the voltage drop in the 4 ohm resistor is 4 ohms times the current I plus the voltage drop in the capacitor, that is minus J 2 ohms times the current I. Okay, and this is equal to 0. And well, we can solve this equation for the current I, and this is equal to 1.118034 with an angle of 56.5650 degrees amperes. Okay, so this is the current that flows through this circuit. And what else? Well, we can compute the average power, okay, the average power of the voltage source, okay, by as follows. No, we have that the power, no, this average power, um, just a moment. This average power is equal to 1 over 2 times the amplitude of the voltage, okay, times the amplitude of the current, times the cosine of the phase angle of the voltage minus the phase angle of the current, okay? But you need to be careful, okay, when computing the average power, because you need to see if the element is consuming or is delivering power, okay, or is supplying power to the circuit. In this case, in order to denote that, we need to use a plus or a negative sign, okay? So for example, typically the resistor will consume power. Okay, so the average power will be positive. But in the case of the voltage source, we need to understand if it is supplying or consuming power. In order to determine that, you need to look at the direction of the current. So here you can notice that the current is entering through the negative terminal. Okay, so based on the passive sign convention, okay, we will say that the power source is supplying power to the circuit if the current is entering through the negative terminal. Okay, so here the current is entering through the negative terminal, so we can say that this element is providing power to the circuit, and we will express that with a negative sign. Okay, so this negative sign is implying that this element is delivering or supplying power to the system or to the circuit in this case. Okay, so the average power of this voltage source is 1 over 2 times the amplitude of the voltage, that in this case is 5, times the amplitude of the current, that is 1.118034, times the cosine of the phase angle of the voltage, that in this case is 30 degrees, minus the phase angle of the current, that is 56.5650 degrees, and these are watts. Okay, so the average power of this element of the voltage source is equal to um, minus 2.5 watts. Okay, so this is the value of, well, this is the average power. Okay, and well, we also need to compute the average power of the 4 ohm resistor. So we know the current, that is the same for all of the elements, but we need to compute the voltage. Okay, so the voltage of the 4 ohm resistor is equal to the current I times the 4 ohm resistor, and this is equal to 4.4721 with an angle of 56.5650 degrees volts. Okay, now we can compute the average power of the 4 ohm resistor. That again, we have 1 over 2 times the amplitude of the voltage times the amplitude of the current times the cosine of the phase angle of the voltage minus the phase angle of the current, and this is equal to 1 over 2. The amplitude of the voltage of the 4 ohm resistor is 4.4721 times the amplitude of the current, okay, that is 1.1180 times the cosine of the phase angle of the voltage, that is 56.56 minus 56.56. Okay, and well, this is equal to the average power of the 4 ohm resistor is, well, if you input all of these values in your calculator, you will see that the average power is 2.5 watts. Okay, and here we have a positive sign. Okay, and well, the reason for that is that these elements, the a resistor in particular, will always consume power. Okay, and we even know that by a positive sign. Okay, in the result of the average power. Okay, in fact, if you add the average power of the 4 ohm resistor plus the average power of the source, this should be equal to 0. And you remember that we have here 2.5 watts, and the average power of the source is minus 2.5 watts, and this is equal to 0. Okay, so this is the way in which you can check if your results are correct. No, the average power of all the elements in the circuit should be equal to 0. Okay, that is a condition that must be met, no, because the energy needs to be consumed by some element. Okay, so this is the way in which you can analyze the problem. Okay, in fact, it is relatively simple. You can use this formula, no, in order to compute the average power. You don't need to solve the integral. In fact, you never need to solve an integral from a numerical point of view. But well, this is the way in which you can solve for the circuit. So I think that we can make another example. So for example, here we have a current source, okay, that has a value of 4 with an angle of 0 degrees amperes. Here we have the 20 ohm resistor. Here we have the inductor, okay. Here we have a capacitor. And here we have another voltage. And here we have another voltage. Okay. And what else we can do? Well, here we need to compute the average power of the elements, but we know that the average power of the inductor is 0 watts, and also we know that the average power of the capacitor is 0 watts, no? This is the average power. But well, we need to compute the average power of the current source and the average power of the voltage source, and also the average power of the 20 ohm resistor. So, well, we need to compute the currents that flows through this element to the through the 20 ohm resistor and through the voltage source. Okay, so I will solve this circuit using meshes. Okay, so I will label this as I1, and this I will label this as I2. Okay, and we can use the mesh analysis. So we have here for mesh 1, you can see that I1 is equal to 4 amperes with an angle of 0 degrees. Okay, and for mesh number 2, well, you need to apply the Kirchhoff voltage law to this loop. So the voltage drop in this inductor is equal to I2 minus I1, okay, times the value of the impedance. That is J times 10 ohms, okay? This is the voltage drop in this element. Remember that the current that flows through this inductor is equal to the difference in currents between mesh number 2 and mesh number 1, plus I2 times the value of the capacitor, that is minus J 5 ohms, plus 60 with an angle of 30 degrees volts, and this is equal to 0. Okay, so this is the result of the Kirchhoff voltage law. And well, you can input this equation and this equation in your calculator, and you will notice that the current I2 is equal to 10.58 dirty with an angle of 79.106 degrees amperes. Okay, now what we can do? Well, we can compute the power of the voltage source. Okay, the average power of the voltage source. Okay, why? Because we know the voltage and we know the current. But you need to be careful about the direction of the current that flows through the voltage source, because you can notice that I2 is flowing from the positive to the negative terminal. Okay, so based on the passive sign convention, we will say that the average power for this element is positive. Okay, but the reason for that is because in this case, the current is entering through the through the positive terminal of the voltage source. Okay, and well, this is equal to 1 over 2 times the amplitude of the voltage, that in this case is 60, times the amplitude of the current I2, that is 10.58 dirty, times the cosine of the phase angle of the voltage, that is 30 degrees, minus the phase angle of the current, that in this case is the phase angle of the current I2, that is 79.106 degrees. Okay, and this is equal to 207.8469. Okay, so this is the average power of the voltage source. Okay, and here we say that it's positive because again, I2 is entering through the positive terminal. Now, what else we can do? We can also compute the average power of the 20 ohm resistor, but first we need to compute the voltage of the 20 ohm resistor. So the voltage of the 20 ohm resistor is equal to 20, okay? 20 ohms times the value of the current I1, okay? And remember that I1 is 4 with an angle of 0 degrees amperes, and this is equal to 80 with an angle of 0 degrees volts, okay? And well, with this information, now we can compute the average power of the 20 ohm resistor, that is equal to 1 over 2 times the amplitude of the voltage, that is 80, times the amplitude of the current, that is 4, times the cosine of the phase angle difference between the voltage, or the phase angle of the voltage, that is 0 degrees, minus 0 degrees, okay? And this is equal to 160 watts, okay? In fact, you can notice that the phase angle difference in a resistor is always 0, okay? And the result of this is always 1, okay? So you can multiply only the amplitude of the voltage and the amplitude of the current and divide that by 2, and you will obtain the average power of any resistor. Okay, so what else we can do? Okay, we need to compute the average power of the current source. So remember that we need to always define the ground of the circuit. So we can say that the ground is always the node that is connected to the negative terminal of the voltage source. Okay, so we can say that the polarity of this voltage source is as follows. Okay, so we can need to compute the voltage of the current source. Okay, so again we can apply the Kirchhoff voltage law to mesh number one, and this is equal to minus the voltage source voltage plus the voltage of the 20 ohm resistor plus the voltage in the capacitor. Okay, and we can express that as well, we can express that as the impedance value times the difference in currents between mesh number one and mesh number two, and this is equal to 0. So you can substitute all the values into this equation. Okay, and here we have well, the value of the voltage source. Okay, and we can substitute the value of I1 and I2 into this expression. Okay, the value of I1, remember that is 4 with an angle of 0 degrees amperes minus I2 that is 10.58 dirty with an angle of 79.106 degrees, and this is equal to 0. Okay, so you only have one incognita, that is this one. So if you solve for the voltage source of the current source, you will notice that the voltage is equal to 185.00726 with an angle of 6.26 degrees volts. Okay, this is the value of the voltage. And with this information, we can now compute the average power of the current source. That is, again, well, we need to be careful about the sign, okay, of the average power. So here you can notice that the current I1 is entering through the negative terminal of the current source. So in this case, we can say that the average power is negative, and we have here 1 over 2 times the amplitude of the current, that is 185.0072 times the amplitude of the current that passes through that element, that is 4, times the cosine of the phase angle of the voltage, that in this case is 6.26 degrees, minus the phase angle of the current source, that is 0 degrees. Okay, remember that the current that flows through the current of the current source is this one, 4 with an angle of 0 degrees amperes. That's why I am placing here the 4, and that's why I am placing here the 0 degrees, and these are watts. And if you compute all of these values, you will notice that this is equal to minus 370, minus 367.8469 watts. Okay. And if you add together this average power plus the average power of the 20 ohm resistor plus the average power of the voltage source, you will notice that the result is equal to 0, no? The average power of the current source plus the average power of the 20 ohm resistor plus the average power of the voltage source is equal to 0. Okay, and this is the way in which you can check if the results that you obtain are correct or are consistent. Okay, and you can verify that by this condition. Okay, if you met this condition, you will you can be sure that the average power that you computed are equal, no? Well, are correct, no? So that's all for these examples. I hope you like it and see you later.